let's take a look at what we did last time. Okay, so we're talking about unions and intersection as part of set theory. So certainly we're coming up with these new ideas, new concepts, and I illustrate them in the simplest possible way. So this is what's on the left. These numbers are the simplest examples of unions or intersections. Okay, so and then the challenge becomes bigger when the actual entities we're dealing with are more complicated. So it could be anything. So then to cover that more or less, we use this illustration that I have on the right. Okay, but once again, you have to understand what it means in addition to these illustrations, and gradually expand this concept from numbers to maybe functions to sets to whatever it is. Okay, so unions, intersections, and what the last topic was I started is just another illustration of this one is of intersections. We talked about that a little bit, but it was, remember, it was inequalities, and so it was entirely about x, and this time, in this example, as you can see, we're talking about sets of pairs x, y, okay, so and those pairs, naturally, they correspond to points, which is good. It again, helps us to understand what's going on, because every pair x, y of numbers corresponds to a point on the xy plane. Okay, so then we realize that that statement over here that we need to find all x, y that satisfy these equations can be written once again like this. So solve the system. What it means, it is literally find the solution set. And what is the solution set? Say x is a pairs xy such that x plus y is equal to 1, and x plus y is equal to 1, x minus y is equal to 1. So finding what that set is, even though finding it is also an ambiguous term, because we have found it. This is it. So what is the solution set? That's it. So then find, what does it mean find? You know what it means. It means in the simplest possible form. So that's why we go on to simplify it, to find something that we can actually say specific about it. So if I try to do the algebra and just ignore the illustrations to begin with, then what I'm talking about is x, y. I can split it, right? X plus y is equal to 1. X plus y such that x minus y is equal to 1. Okay, so split it into sets, and and then take the intersection. Okay, so x, y's are, just read what we have here. We're looking at pairs x, y that satisfy the first equation, and they satisfy the second equation. Okay, so then if we take all of those x, y's that satisfy the first equation and all that satisfy the second equation, put them together, how it will be the intersection. Okay, so you can illustrate this literally with, so the solution would be pretty much almost all we see. We can kind of simplify it slightly, but really not by much. But if you illustrate it with on the xy plane, that helps. So the first one, x plus 1 is equal to 1 is this one, right? 1, 1. Okay, and the second one is that one. X minus 1 is equal to 1, so x minus 1, x minus 1, y is equal to x minus 1. This one. Am I right here? Okay, and then once you have illustrated this way, you can now point out what the intersection is, and turns out to be a single point. So once again, I did not address how we find that point, all the algebra that's involved. I mean, that's we don't care about that much. We don't care about at this time how to find something, right? But rather what is that we're looking for. And what we're looking for whenever we solve a system of equations or one equation or inequalities, it is find all x's or x and y's that satisfy those equations. And when you have it is that symbol over there, over here, is usually means and. So that's a lesson about mathematics. Whenever something is there are all these symbols and nothing else. All the symbols stand for something, and then you have to figure out what is that. You can kind of have to deconstruct it and see what every symbol means, or what every word means, what solve means, what is you have two inequalities side by side. Almost invariably it is the same, it is and. Both of them have to be satisfied simultaneously. You have three equations, you'll have three equations that would have to be satisfied simultaneously. The outcomes are not to be expected always to be this. So if instead of this x plus 1, x plus y equal to 1, x minus y is equal to 1. Okay, so this gave us the single point. Okay, why? Because it turns out that the first equation represents a straight line, the second equation represents a straight line, and then they intersect, but it doesn't have to be this case. Doesn't have to be this way. I could have x plus 1 is equal to 1, x plus y is equal to 2. That's another equation. So what's gonna, but it doesn't matter. It doesn't matter if you understand the equation correctly. I hope we do now. Then it doesn't really matter what those equations are. You look at them in the same manner, and only the very last moment, if you want to do illustrations, you figure out what the answer will be. What is the answer? The first equation is the same. What's the second equation? Almost identical. What? Parallel. It is parallel, as a matter of fact, yes. So the second one is this. Okay? So then, in other words, in addition to logic, you do either geometry or algebra to actually solve the problem. But the question now becomes, how do we write the answer? What's the answer? The solution set. What?
There is no.
That's not the good way to put it. How do we put it?
There is no solution.
That's one way to do it. X is the null set. Yes. Okay. So so there are no such xy's that satisfy both equations, and we'll also say the intersection is empty. So the intersection is the empty set, or the intersection is empty. So, and that's the answer.
D and E like does not exist, or would you just rather?
I would rather not. So yeah, so we're leaving it behind.
Okay.
So we want to be very, very careful with that, with the language that we use. So here's another one. What about this one?
Isn't that the same exact thing?
It is the exact same line.
Line, yeah.
Okay, so then once again, if I try to plot this one, looks like this. The second one turns out to be the same thing. So okay, so what's the answer then? What? No. We are not talking about numbers. Look at the solution set that we established here. It's we talk about pairs.
Do you put like a union in between them, like?
No. It's still this still works out. So have two equations. To solve the system is to find the set of solutions of the first equation, of the second, take the intersection because they have to be satisfied simultaneously. Two conditions have to be satisfied simultaneously, but it's the same condition. So let's say this is A and this is B. So X is A intersection B, except A is equal to B. So what do we have? A intersection A. What?
Could you even
It's the same thing.
Could you come up with another term to represent A and B and just say C and say that C is
No, I
equal
want
to
just
A and
just
B?
simplify. Intersection A, what is it?
A.
It's A. It's just that's like algebra. Like 1 multiplied by 1 is 1.
Right.
Like that. So you don't
Yeah.
say, what is 1 times 1? You don't think about it, try to invent a new number for it. It's 1.
Okay.
Right? So once again, but back to the question that the solution was suggested. It's not about the numbers. It's about pairs of numbers. And if we have found the solution for A, that is the orange line, that is the answer. So it's not everything. So we're talking about pairs of x and y. If you take all pairs of x and y, you'll have the whole plane. Okay? So just the point being that the answer is non-trivial. It is in fact, for example, these are solutions, right? The points on the line are solutions, but say, well, this one not a solution. So you have a bunch of not a solutions, and only a line is the solution. So there is a point to it. And that when you're solving systems of equations, it is possible that, as we know, you might end up with infinitely many solutions, and you have to point out what that set is, and so we did, in a way. So the answer would be simply, like x plus y is equal to 1. There is really no way to simplify it any further, but illustration certainly is helpful. Okay, so if you have systems of equations, as I said, you never end up with or. It's always and. So even though it's seemingly identical, not identical, but seemingly equally important concepts, logically speaking. But if you're solving equations that you probably have restrictions, and the restrictions would have to be satisfied simultaneously, so you have and. So that's the situation in algebra, but you can certainly make up problems. And we actually did look into one problem just to refresh your memory. Say x larger than 5. Okay, so solve it. Okay, so then so remember how it works out. You actually split into two equations: x larger than 5, x less than -5, and you have or there. So either one or the other would be good. Equally good. So and then it is the same as taking the union. Less than larger than 5. Okay, so these are illustrations of intersections and unions. Let's define them. It is actually they can actually be defined. So suppose A and B are sets, then x belongs to A intersection B if x belongs to A and x belongs to B. So that's the definition of then the intersection is defined by okay, so x belongs to the intersection whenever x belongs to A and x belongs to B. And then similarly, so once again we have two sets. Then the union, their union, is defined by, well, you can guess how it is defined. X belongs to A union B if what?
X belongs to A or X belongs to B.
Right. So that's it. So that is the definition. The two definitions of those sets. So it's purely set theoretic definition. So we're not talking about numbers. We're not talking about sets, functions, anything. Any two sets can be worked out in this fashion. Okay. So you can see how they match up as we planned it for them to be intersection and union or. Okay, so either one or the other. Okay, so whenever it is, if you feel confused, well, those illustrations certainly are helpful. How you combine those, so that's typically how you illustrate things in set theory with those circles or ellipses, and how they intersect, how they or the union look like, and that's what we're going to do for a little while. Okay, so empty sets. Well, let's combine. Let's just do this in a set theoretical way for a moment, and combine them with the empty set. So suppose. So these are the definitions. Let's see if we can do mathematics at its most abstract. So. How about this? What if B is empty? Then what? The intersection is also empty. So how do we handle the empty set? It has no elements. In other words, if you pick an element anywhere, it does not belong to the empty set. So I guess maybe so the empty set. Well, let me put it this way. Probably worthwhile. So X, then X does not belong to the empty set. Okay. This is pretty much the definition of the empty set. So whatever element you pick anywhere, it does not belong to the empty set. So you don't say that it has no elements. It's a little bit informal, and if you do any kind of logic, this might be more helpful. So if you pick any element anywhere, X does not belong to the empty set. Okay, so that's if we want to prove that the intersection of any set with an empty set. Well, it certainly stands to reason. You can just imagine yourself that the intersection at the right top corner. What if this is B and this is empty? It has no elements. So a whole set intersection with something that's not there. Is there any element that belongs simultaneously to A and B? It cannot belong to B because there are no elements. So there, you fail right away. Okay. So take X. Okay. Then X does not belong to empty set. Then X does not belong to a intersection with empty set. Because X has to belong to both. If it does not belong to one, it doesn't belong to both. There, and you have that. So that's the proof. If the intersection of any set with an empty set is an empty set. Okay. What about union? B is empty. Then what's the union? What?
Just A.
Just A, that's right. Okay, so the union of when you set with the you don't add, you can certainly think about it, like there are no nothing is being added to A, and that's why it has to be A. If you want to prove it, so take X, then X does not belong to the empty set. No, let's take X that belongs to A, then it does not belong to the empty set. Then X belongs to the empty set, union A. Okay, there you go. So because it has to belong to one or the other, right? So if it belongs to A, then we're okay, even though it does not belong to the other. So so in that fashion, you can do a lot of other things. But before we do the next one, I just want to illustrate that it is very important concept of disjoint sets. A and B are called disjoint. If they have empty intersection. Okay, so let's illustrate this. Well, first of all, it's very easy to illustrate it graphically. Well, A and B, they have nothing in common. That's an informal illustration. I want to illustrate it with examples. So as an example would be odd and even. A is odd numbers, B is even numbers, so they do not overlap. Can you think of anything else? What? Prime and composite, right. Prime composite, okay. Anything else? What? Okay, yeah. I suppose. Well, you're not supposed to do one, at least at the moment. Even if you come back from death, at that moment you are dead or alive. You cannot have both. Yeah, so anything else from outside of mathematics? These are, by the way, these two, why these examples are imperfect in a sense, they're mutually exclusive, they are complementary, right? These are complementary. It's important, but because there is nothing else. Either odd or even, there is no third possibility. Prime, composite, no third possibility. Dead, alive, no third possibility. So can you think of something in mathematics? Let's start with mathematics. That two examples that are not complementary but disjoint. Like this. So this example is this is the square, is all the possibilities, and then there is still possibility that neither A nor B.
So we're looking for mutually exclusive?
Disjoint, mutually exclusive, yes, but not complementary. Disjoint, not complementary.
So disjoint is two sets that don't overlap?
Right.
Okay, so isn't that what a complementary does?
No, complementary means that there is nothing else left, so they're fully complementary. There is nothing in between.
So two things don't overlap, but there's other options too?
Yes, right. That's what I'm asking.
Okay, so chocolate ice cream, vanilla ice cream, but
Yeah,
strawberry ice cream? I don't know.
Yeah, that's right. Yeah, it is actually much more common to have two possibilities, different possibilities, non-overlapping possibilities, but they are not complementary because there might be more than two choices. So the easiest example is in mathematics would be, I think, say divisible. What should I pick? Divisible by 3. And remainder 1, remainder 2. Well, maybe it's not such a good example, but we can split our integers into 3 based on the remainder. So this is division by 3. Okay, and then you can split all the integers into the ones that are divisible by 3, the remainder is 0, those that have remainder 1, and those that have remainder 2. Okay, so certainly they do not overlap, even though it needs to be proven. So we need to prove that it is indeed the case, and but at least it is certainly intuitively clear that you cannot have the remainder simultaneously 0 and 1, but you also know that there is a third possibility, a remainder of 2. So anyway, we'll do more of this. Take another look at the homework. Maybe we'll talk more about it if necessary.